Welcome to the Explainer. Sometimes the biggest ideas about the universe are hiding in plain sight, like in a simple physics worksheet. That's what we're going to do today. We're going to take these problems and turn them into a story about the one thing that makes everything happen: energy.
So let's start with a really big question. What does it actually take to change anything? To lift a book, to launch a rocket ship, heck, just to get yourself out of bed in the morning. Turns out there's one single answer that covers it all. Any guesses?
And the answer, in the world of physics, is work. Now, I know what you're thinking. Going to work, right? But in physics, this word means something so much more fundamental. It is, quite literally, how the universe gets anything done.
All right, first up, doing the work. Let's dig into what physicists really mean when they say that.
Okay, so here's the deal. Work is just the official term for transferring energy. And it's really specific. It only counts as work if you meet two conditions. One, you've got to apply a force, a push or a pull. And two, that force has to actually move the object a certain distance. That's it. The formula couldn't be simpler. Work is just force multiplied by distance.
So let's make this real with one of the problems from the worksheet. Say we're pushing a block. We push with 80 newtons of force. Don't worry, that's just how we measure force. And we move it 20 meters. You just multiply those two numbers together, boom, 1,600 joules. And a joule, well, that's our special unit for energy. So that 1,600 isn't just a number on a page, it's the exact amount of energy we literally just pumped into that block.
Okay, but what happens when it's not so simple? Like, what about a tug of war? You've got a girl pushing one way, adding energy, that's positive work. Then you've got a boy pushing the other way, basically trying to take energy away. That's negative work. So who wins? Well, we look at the net work, the grand total. And here, the push to the right is a little stronger, so in the end, the box still gains 24 joules of energy. It's the final score that matters.
Okay, so we've done the work, we've transferred the energy, but where does that energy actually go? Well, it basically shows up in one of two main flavors. You've got stored energy, and you've got energy of motion.
First up is potential energy. I love this one. You can kind of think of it as what-if energy. It's energy that's just stored up, waiting for its moment. It's all about an object's position or its condition.
And we see a couple of perfect examples right here. Look at the diver high up on that platform. That's gravitational potential energy. The higher she goes, the more energy gravity stores in her. Then you've got this compressed spring. That's elastic potential energy just waiting to spring back. See? Stored energy. And the other side of the coin, that's kinetic energy. This isn't what-if energy, this is right-now energy. It's the energy of motion. Plain and simple, if something's moving, it has kinetic energy. And the formula for it, K equals 1/2 mass times velocity times squared. That little squared part is going to be a very, very big deal. Yeah, that velocity squared part. Let's talk about why it's so important. Take this roller coaster. It's got a mass of 500 kilograms, and it's zipping along at 20 meters per second. Now, here's the question. What happens to its energy if you double its speed, if you just kick it up to 40 meters per second? You might think the energy just doubles too, right? Well, not exactly. Check this out. When you double the speed, the energy doesn't double. It goes up by a factor of 4. It quadruples, from 100,000 joules all the way to 400,000. That's the power of that squared in the equation. It's not just some weird math thing. It's the reason why speed has such an explosive impact on, pretty much everything.
So now we have these two types of energy, potential and kinetic. And this is where it all comes together. Because these two aren't separate things. They're constantly trading places, locked in this amazing dance that's run by one of the most important, unbreakable rules in the entire universe.
And here it is, the law of conservation of energy. Energy cannot be created or destroyed, only transformed from one form to another. It's so simple, but so powerful. It means the total amount of energy in the universe is fixed. It just changes its outfit, It swaps from potential to kinetic and back again, but the total amount never, ever changes.
Let's watch this happen with this skier. She's at the top of a 40-meter hill. For just a split second, she's not moving. At this exact moment, all of her energy is potential energy. It's just stored up, a gift from gravity, thanks to how high up she is.
Yep, if you look at her energy pie chart right now, it's 100% potential, all stored up, ready to go.
But then she pushes off. As she skis down that hill, gravity is doing work on her, and that potential energy starts transforming.
It's turning into kinetic energy, the energy of speed. And by the time she hits the bottom, her height is 0, so her potential energy is gone. It's all been converted. She's now 100% kinetic energy. The total amount of energy never changed, it just switched teams.
Okay, now that we have this incredible law in our back pocket, let's use it to solve one last really cool, kind of counterintuitive puzzle.
All right, picture this. You're on top of a building. You have 3 identical balls. You throw all 3 of them with the exact same speed, but you throw them in different directions. One goes straight up, one goes straight down, and one goes out horizontally.
So here's the question for you. Which ball is moving the fastest right before it hits the ground? Think about it. The one thrown up, that has to go all the way up and then come all the way down? The one thrown down, which gets a head start? Or the one launched sideways? What do you think?
You ready for this? The answer is, they all hit the ground with the exact same speed. It seems impossible, right? But it's all because of that law of conservation of energy. Let's think it through. Do they start at the same height? Yup. So, same potential energy. Do they start with the same speed? Yup. So, same kinetic energy. That means their total starting energy is identical. And if the total energy at the start is the same, the total energy at the end has to be the same. By the time they hit the ground, all that energy has become kinetic, so they all must have the same final speed. Mind-blowing, right?
But this brings up one final, nagging question. In the perfect world of physics problems, everything works out neatly. But in the real world, a skater on ice doesn't go on forever, right? They slide to a stop. Their kinetic energy just seems to disappear. So if energy can't be created or destroyed, where in the world does it go? That's a great question, and a story for another explainer. Thanks for watching.